We're going to continue our discussion now about strategies to find the area beneath a curve. So I've drawn this graph of negative x squared plus 4x plus 5, kind of sketched it out here, marked some major points on the graph. So our goal is to estimate the area beneath the curve. And I'm going to go ahead and pick an interval here just to kind of make it easier for us. So suppose I want to estimate the area underneath this curve between 1 and, say, 4. So I'm looking at this region right in here. This is the region I'm interested in knowing what that area is. So we discussed in our last class that we could use rectangles and left and right hand sums to get an approximation for this area. So let's look at an example here. Let me go ahead and use rectangles of width 1. So I'm going to start here. I'll do the left-hand sum first. Let me use purple for that left-hand sum. So I come up to my graph, grab the function value, and I'm going to go over a distance of 1. So let me get over here so I can draw this as straight as possible. So I go up to the graph, left-hand corner, and then draw to the right, and I get this rectangle here. That's my first rectangle for my left-hand sum. So I'm going to do left-hand sum. The width of my rectangles are going to be 1, so it's going to be 1 times, now I'm going to add up the height. So the height of this rectangle is 8. Okay, let me do the next rectangle. I come all the way up to the function graph. It's right up there, 9. Go right 1 unit. So let me draw this as straight as I can. Right 1 unit. And so the height there is 9. So I've got this rectangle. And then finally, for the third rectangle, I'm going to go up to the graph right here at 8, go over 1 unit, continue on up. I get this area. And the height of that one is also 8. So my left-hand sum estimate for the area is 8 plus 9 plus 8, which is 25. So I estimate that the area beneath this red graph between 1 and 4 is 25. Now you see in some cases it was a little bit short, right? We have this extra area that wasn't included. In some cases it was a little bit more. Here we have this extra area there, and here we have quite a bit of extra area right in here that was included. So this might be an overestimate, but it's an estimate nonetheless. That was the left-hand sum. So let's go ahead and do the right-hand sum. Again, our upper right corner is going to touch the graph. I'm interested in that little interval, so I'll do that one in orange. So instead of starting at 1, I'm going to start at 2, go up to the graph. There it is. And this time draw to the left. So now I've got this rectangle. I'll highlight that one in orange. So again, the rectangles are going to have a width of 1. This first rectangle has a height of 9. Now I'll go to my next rectangle. I go over to 3, go up till I get to the graph right there, and go over 1 unit. So now I'm looking at this rectangle right here. So right below that. And that has a height of 8. You can see I've been drawn perfectly. These are all supposed to be the same height there, sorry. So that's going to have a height of 8. And then I'll go finally over here to 4 until I get to the graph. Draw that horizontal line. I'm looking at this rectangle, and it has a height of 5. So my estimate of the area is 9 plus 8 plus 5. That turns out to be 22. So my overall estimate between the two of those is that the area is somewhere between 22 and 25 is my overall estimate. Now, it'd be great if we could get more precision, and we could certainly draw more rectangles, and we could get more precision as we cut those rectangles in half. We'll reduce the error. in both of those cases. We could continue to do that, but it becomes increasingly cumbersome to actually write or draw the rectangles and do these calculations. Becomes messy. But we'd love to do more rectangles so we could actually get a more accurate estimate on the area. So what we're going to do is we're going to introduce some notation that represents the idea of doing infinitely many rectangles of infinitely small width, infinitesimally small width. So the left and right, some ideas here we'll be using, but we're thinking about the idea of doing a bunch of rectangles, very, very narrow, small width. So I'm going to use this notation. Delta x is the width of the rectangle, and dx is going to be an infinitesimally, that's not a word you use every day, small width. Okay. So delta x is in general the width, but when we're going to let that width become an infinitesimally small, we're going to call it dx. Then this notation, this is the Greek letter sigma, will means to add up. So basically when you see the sigma notation, it says add up a bunch of things. We'll often use it with some indices, which I'll show you here in a moment. So let me go ahead and do that sigma notation again. Oops, if I can draw it right. There we go. My sigma notation that way. And I'm going to go, for example, here, I equals 0 to n minus 1 f of x sub I times delta x. And that looks crazy. There's a lot of craziness going on there. I'll explain what that means. But this is representing the idea of a left-hand sum. This is our formal notation for left-hand sum. Right here is this notation with the sigma. It says I'm going to add up a bunch of function values. These are the heights of our rectangles here, and then multiply by the width of the rectangle. So let me use this notation for what we've got over here. So I had my left-hand sum was equal to, the way I would write that was sigma I equals 0 to n minus 1 for f of x sub I. And my delta x in that case was my width, was 1. All right, what would be the f of x sub I? Well, this tells me, and I should have actually said here, instead of n, I should write, how many rectangles did we have? 1, 2, 3. That should be a plus there, by the way. 3. So this is just going to be 3 minus 1 will be 0 to 2. So this notation means f of x sub 0 plus f of x sub 1 plus f of x sub 2. That's what this notation tells me, and each of those are being multiplied by the 1. So times 1, times 1, times 1. So that's what that notation means. Well, the f of x sub 0 is the 8. The f of x sub 1 is the 9. The f of x sub 2 was the 8 again. So that's how that notation works. For the right-hand sum, we would write it like this. The sum going from 1 to 3, and f of x sub I times delta x. And again, that means f of x sub 1, that's where we started, plus f of x sub 2, plus f of x sub 3. Again, our delta x is 1, so that's all times 1, which were the values. Our f of x sub 1, we saw from before, was 9. F of x sub 2 is 8. And f of x sub 3 was the 5. So that's how this notation works. And so again, we're going to move to the idea of having infinitely many rectangles. Let me go and show you that with a table of values that might help make this a little bit more clear. So I'm going to go ahead and erase my graph and replace it with a table of values. All right, so here we are, x, f of x. And let's go and look at the values. Remember, we were going between 1 and 4, I think is where we were going. 1 and 4, that was the values we were interested in. So let's go ahead and do 1, 2, 3, 4. And remember, at 1, the height was 8. At 2, the height was 9. At 3, the height was 8. And at 4, the height was 5. So those were the values we had. When we can start labeling this, we'll start at the top here. This will be x sub 0. This will be x sub 1, x sub 2, and x sub 3. So we'll always start with the x sub 0 being the first data point. So we were looking, remember, at this one on that interval from 1 to 4. That's where we were looking at it. So x sub 0 will always be your first value. X sub 3 will always be your ending value. And for the left-hand side, remember we used these 3 function values that will correspond with x0, x1, and x2. You can see that right there. And then for the right-hand sum, we used these 3 function values, the 9, the 8, the 5, that correspond with x1, x2, x3. You can see that notation right there. Okay. So let me then continue to work with that notation, represent this idea of having infinitely many rectangles. So I'll use this notation now, which we've set up, can be used to represent the left and right hand sums as follows. We have the limit as n goes to infinity of, we have our summation notation, and I'm going to have I go from 0 to n minus 1. This is our left-hand sum of f of x sub I delta x. So here's the heights of our rectangles. There's the width of the rectangles. We're adding up a total of n of them, going from 0 to n minus 1. But we're letting n go to infinity. If I use infinitely many rectangles on the left-hand sum, I'm going to represent that by integral of f of x dx. So this is a stretched out s, if you will. We call this the integral sign. Integral sign. And so it tells us we're going to add up infinitely many rectangles of height f of x. And of course that varies as x changes. And then this dx represents that infinitesimally small width. So think of this as all these adding up all these rectangles, but there's infinitely many rectangles. That's the notation there. Well, it turns out that if you're using infinitely many rectangles, this left-hand sum, which is, oops, I should just write this right here is the left-hand sum before we put the limit on it. And the right-hand sum, let's go and put the limit on that, of going from that first to 1 to n of f of x, so I delta x also equals the integral of f of x dx. So what we're saying is if we do the left-hand sum or right-hand sum and we're using infinitely many rectangles, we will get the exact area. And both the left and right will be the same values. So that's powerful. So this is the notation we use, and visually think about this as the height of the rectangle and these widths of these rectangles. So this is called integral notation. We'll be using this extensively to represent the height or the areas underneath curves. All right, so we will I'll erase this and we'll continue our discussion. Okay, let's return to our function. F of x equals negative x squared plus 4x plus 5. If I want to represent this, so remember my task was find the area between f of x and the horizontal axis between x equal 1 and x equal 4. That's what we wanted to do. So find the area between f of x and the horizontal axis between x equal 1 and equal 4. How do we represent that using that integral notation? And so the way we represent that is this. We're going to sum up all those areas of those triangles. The height of the triangle is going to be given by f of x. The width we're going to represent by dx. That's the infinitesimally small width. And the fact that we're going between 1 and 4, we can capture right here. These are called the limits of integration. So this tells me I want to find the area beneath the curve f of x and the horizontal axis between 1 and 4. Now here I should make a comment. This calculation will return the area as long as the function is above the horizontal axis. If the function's below the horizontal axis, it'll actually return what we call the signed area. So it'll be the area that'll have a negative sign on it. So this calculates the area above, when the graph is above the x-axis, it calculates the area between the x-axis and the graph. If it's below the x-axis, it'll calculate the area and then multiply that area by -1 and give you the signed area. This will give us the area between f of x and the horizontal axis between x equal 1 and 4. So this is that notation. So what is that area? And we'll be getting to that later on in terms of the techniques by which we can figure out what that exact area is. Our estimate was somewhere between, we'd estimated, remember, with our left and right hand sums, between 22 and 25 was our estimate for the area. All right, so the key thing I want you to take away from this is that this represents the area between the curve and the graph of the horizontal axis, as long as it's the functions above the horizontal axis. It's signed area otherwise. Taken together, if you've got a graph that goes above and below in the same interval, then this becomes the sum of the signed areas. And I'll go and write that. The sum of the signed areas. So it takes all the area above the horizontal axis, and then subtracts all the area below the horizontal axis on the interval, and that's what this will calculate for you. All right, we are going to continue our discussion about areas beneath the curve. This time I'm going to use Desmos, though, because it's going to be a very powerful technology to help you understand what's going on and also to calculate these areas. So I have the same function I worked with earlier, f of x equals negative x squared plus 4x plus 5. And the first thing I'd like to do is shade the region between 1 and 4. We had indicated that that was the region where we were interested in figuring out the area. Let me go ahead and adjust my steps there on that horizontal axis so that you can see. I don't need the minor grid lines, and let's also adjust that for the y values. There we go. That will look a little bit better. I'll make it a little bit bigger for you. There we go. So I'm interested in the shaded region between 1 and 4 only. So to draw that, I'm going to first of all tell Desmos that I would like the y values to be between 0 and my function f of x. And that's going to shade that overall region. So you can see it's shaded that region for me. But I'm only interested in what's going on between between 0 and, or 4. Actually, it was 1 and 4. So let me go and fix that, between 1 and 4. So there we go. Now it's actually shaded the region I'm interested in. and I wanted to know what the area of that region is. Now we can see these boxes here. If you look at the shaded boxes, each one has a area of 1 unit. And if we count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I've got 21 full ones and then some partial ones. And so, yeah, so our estimate was 22 to 25 is right in there. We can kind of see that visually. What's really cool about Desmos is Desmos will calculate that area specifically for us as long as we tell it what we want it to do. So I will go ahead and do that now. When you bring up Desmos, you're going to go to Functions, and you're going to scroll until you see the integral sign. And there it is, the integral sign. And it's asking me for the limits of integration. So between what values do I want to find this area? So I'm going to do 1 and 4. And I said, well, what's function? Well, I named my function f of x. So let me go ahead and do this for my function f of x. And then I need to tell it dx, because that was, remember, the width of our rectangles there. And it says that the integral of f of x dx is 24. So the exact area, not an estimate, the exact area is in fact 24 here. So that's pretty cool. What if I wanted to figure out the area of another region? So what if I want to know what the area of the region is from -1 up to 1? That's a piece I didn't have. So let me go ahead and draw that for us. Let me do 0. Actually, let's do 0 is less than or equal to y is less than or equal to f of x. But this time, let's do it going from -1 is less than or equal to x, which is less than or equal to 1. So now it shades that region, so you can see that area. And I'm going to ask it now to find the area of that region. And that goes from -1 up to 1 is the region I'm looking at. Again, my function's f of x. Those are the heights of the rectangles, and then dx is the width. So the area of that region is 9.333 repeating, or in other words, 9 1/3. That's kind of interesting. So I know the area of the gray region is 9 1/3. The area of the green region is 24. What about that remaining region between 4 and 5? Let me go ahead and graph that. So I want, again, the y values to be between the horizontal axis and f of x. And I'm interested now, though, between 4 and 5. So I've shaded that region. You can see the blue region now. Let me go ahead and calculate the integral for that. So again, I want to find the area there. The integral from 4 to 5 of f of x, that's the height, dx, and it tells me that overall is 2 2/3. Well, what if I wanted the entire region, the gray, the green, and the blue all together? So going from -1 to 5. So I can do that integral. And integral, I want to go from -1 all the way up to 5. So I want the entire region of f of x dx. And we can see that that total is 36. Now, it should be no surprise to us that if we were to add up those individual areas, the gray area, the green area, and the blue area, we would get 36. And you can see that the 24, and then we've got the 9 and the 2, and then the 2/3 and the 1/3 add up to 1. So altogether, those all add up to 36. So that's interesting. We can add up integrals as well and get the corresponding areas. So this just illustrates how to use Desmos to shade regions and also to calculate those areas.